Good. Yeah. I think, yeah,
Good.
it's working. Yeah, thank you.
Cool. Thank you. You're an experimentalist, Takeshi.
No.
You're not. You're a theorist. Okay, I see. All right. So, but you have ideas on how to detect
Yes.
these things. That's very
That's
interesting.
from the theory.
Well, I'm very interested in these things. You know, my dream is that uranium ditelluride is both topological and time reversal breaking, which would mean it's outside the table.
Okay.
Impossible. There's no broken time reversal 3D topological superconductor, according to me.
Yeah.
Yeah.
So far, yes.
Yeah. But I'm hoping it will. It will be. Okay, guys. So, good afternoon. Go ahead and pat my hands. Okay. The best is yet to come. And for our last talk today, we have Takeshi, who is kindly agreed. Nobody wants the last slot, of course, but his talk will be truly excellent, I'm sure, and it will be well worth waiting for. He has come over from University of Osaka, and he's going to tell us about the challenges of trying to detect and characterize topological surface states, not only in uranium ditelluride, but also in superfluid helium-3, which is the only truly guaranteed topological state of matter apart from the quantum Hall effect that we know of. So, welcome.
Thank you. Thank you for kind introduction. And also, thank you for all organizers for inviting me to this wonderful place. I really enjoyed our program in this week. So I'm going to discuss about what is the fingerprints of the topological superconductivity in uranium ditelluride and helium-3, especially from the theoretical side. Okay. So let me start to thank my collaborators. Especially, I'd like to thank these two guys, UTe2 and Yoi Ohashi, who are main players in this talk. And also, I'd like to thank these people, Satoshi Fujimoto, Yukio Tanaka, Ryo Anai, and Jim Source for long-term collaborations. Okay, so recently the concept of the topology has been expanded to the various fields of the condensed matter physics, and especially the theory for the topological phases of matter have been greatly developed during the past 10 or 20 years. And nowadays you have a powerful scheme to automatically identify the topological nature of the system. For instance, in the superconducting material, once you have information of the Cooper pairs and normal electron, and then you can automatically judge whether this is topological or not. So, but challenge remains because usually in strongly correlated material, it is difficult to identify the pairing symmetry pairing mechanism from the first principles. So we cannot, it's difficult to know the information of Cooper pairs from first principles. So here, I'd like to focus on surface physics instead of the bulk physics, because the non-trivial bulk topology appears on the surface through the bulk edge correspondence. And then I'd like to ask, can we narrow down the pairing symmetry by observing the response of the surface state? Or in other words, what can we learn about the bulk physics from the surface? So this is my motivation. And in order to address this question, here I'd like to focus on these two systems, uranium ditelluride and helium-3. And because not all, but the most spin-tripped superconductors can be topological in some sense. And UTe2 is one of the strong candidates of spin-tripped superconductors. But of course, the pairing mechanism and gap symmetry, they are still controversial. So identifying surface state and topological superconductivity will help to solve these puzzles. And another target is the helium-3. This, of course, spin triplets period superfluid. So the topological property of helium-3 essentially same as that in UTe2. But the situation of helium-3 is bit different from the situation of UTe2 in the sense that bulk superfluid properties like gap symmetries and pairing symmetries, they have been well understood. So, but in order to address the surface physics, you need to establish local flows because helium-3 atoms are charge neutral, right? So there's no electric way to observe the surface physics. So this is my motivation, and here is the outline of my talk. So first, I'm going to emphasize that UTe2 is a topological superconducting state protected by crystalline symmetry. And then I'm going to show you our recent work on undirect spectroscopy, which was motivated by the recent STM measurement using a superconducting tip. Okay, so then I'm going to discuss about what is a signature of the topological superconductivity. And then lastly, I'm going to share with you current status and the future prospect for detecting the topological surface state in helium-3. Okay, so now let's start to briefly introduce the topological surface state in UTe2. Okay, so maybe at the very beginning of this conference, several speakers gave a beautiful talk on UTe2, so maybe I can skip the basic introduction. But here, what I want to emphasize again is that several experimental evidence indicates that this material is really unconventional and a strong candidate of spin triplets superconductors. And we are interested in the topological nature. So when we discuss the topological nature of superconducting material, you need information of the shape of the film surface. This is very important information to determine the topological properties. And recently, a couple of experimental groups reported observation of the quantum oscillation behavior, namely the Dohas-van effect. And this frequency of oscillation frequency is consistent with the existence of the psi two-dimensional film surface. And actually, this calculation reported the existence of the two electron sheet and the two hole sheet, which are elongated along the shear axis. So, and also, of course, we need the Hamiltonian, but for simplicity, we take the very simple form of the Hamiltonian. We only look at the two orbital degrees of freedom in uranium atoms. So this two orbital model Hamiltonian was originally suggested by the Shishido and Daniel Alderberg, and we use this simple Hamiltonian. And this is my Hamiltonian for the normal electrons, which consists of the intra-orbital hopping and inter-orbital hopping. So this is minimal Hamiltonian that captures the essential part of the topological superconductivity in this compound. And the crystal of UTe2 belongs to the D2H point group symmetry. So the possible gap symmetry are classified in terms of the four irreducible representations. And two of them are fully gapped. And the other, B3U and B2U, they have point nodes on the surface of cylindrical film surface like this. But to be precise, B1U may have a point node along the KC direction, but my film surface is open to KC direction, so the point node doesn't appear in this cylindrical film surface. So in that sense, B1U and AU has a fully gap pairing state. So maybe it's difficult to distinguish them from the, for instance, bulk.
I just have a question.
Yes.
So D2H is the crystal symmetry, right?
Yes, sir.
So we understand that an unconventional superconductor can have any gap symmetry, right? It's just going to break the symmetry in many cases of the underlying lattice. So why do you limit it? Why don't we have an EG, or why do you limit it to those gap symmetries?
Yes. First, I want to simple, I want to keep simple,
Okay.
yeah.
Okay.
And here I also focus on the zero magnetic field. So of course, in the presence of the magnetic field, this UTe2 is lower to yeah, another crystal machine.
Okay,
Yeah.
so it's just to simplify. so,
Simple, yeah, very, very simple.
That's
We
great.
start from the very simple.
That's good. Thanks.
Thank you. And okay, so yeah, this is a pairing symmetry we consider here. And yes, all of these four pairing symmetry can be topological. And but actually, okay, so all these pairing symmetry can be classified to the so-called D3 topological class. And D3 topological class, the topological number is defined by the three-dimensional winding number defined over the entire Brillouin zone. But this can be non-trivial only when the time reversal invariant point in the Brillouin zone is enclosed by the term sub, auto number of the term surface. But my term surface is open to the KZ direction. So this topological number becomes trivial. But nevertheless, we can define another type of the topological invariant in a lower dimension thanks to the crystal line symmetry. Let me explain more detail.
Sorry, just one question about Laura's question. So D2H is a point group of this crystal, right?
Yes.
So then I think these are the only possible treatment of the parameters. This is exactly the same
Yeah,
point group.
this is a one dimensional order, one dimensional unit.
Well, if it's triplet, it can only be those four, and they are all one dimension. It's exactly the same point group analysis that we did for lanthanum nickel gallium 2, which is the same point group.
Okay. So yeah, let me explain the topological nature of this compound. So first, let me introduce a crystalline symmetry operators, AU, which includes a twofold rotation, mirror reflection symmetry, and so on. And combining this U with the time reversal T and the particle Hall exchange operator C, you can define the chiral operator, which is anti-commutable with the Hamiltonian. I skip the detail, but once you have this kind of chiral operator, it is straightforward to define the winding number along one particular momentum path on the symmetric plane. For instance, if you have a mirror reflection symmetry, then you can define the winding number along one dimensional momentum path on this mirror invariant momentum plane. So anyway, if you have this winding topological number, you can judge whether each topological, each irreducible representation is topological or not. And actually, in the AU pairing state, which is a fully definite pairing state, on both 100 and 010 surface has a gapless surface under the bound state, which has a cone-like dispersion. So let's say Majorana-cone. And these Majorana-cones are protected by the C2 rotation about the A axis and B axis. And other irreducible representation has a zero energy flat band Fermi up on the surface, which are protected by different types of the mirror reflection symmetry. So, I'd like to emphasize that these Majorana-cone and Fermi arcs are very robust, even and can survive even if each of the U and T are explicitly broken. For instance, by applying magnetic field, you can break the mirror reflection or time reversal symmetry. But even in such a situation, these Majorana-cone and Fermi arc can survive as long as the combination of the UT is preserved. So in that sense, this topological surface state can be protected by the magnetic symmetry, combination of the crystal line and the time reversal symmetry.
A question?
Yes.
I think these are when you call them arcs, do you mean they're complete circles or
It's
arcs?
just a line.
Just a line?
Yes.
So what defines the, for example, in a vial, in a vial semi-metal, you have the ends are defined by projections from the vial cones. But what defines the ends of these arcs?
Yeah. Actually, the end of the arc is absorbed at the point node in the surface beyond. Okay, so okay, so here is the bulk superconducting. Yeah.
Yes.
We have point node here and here,
Yes.
and permeate appears connecting these 2 point nodes.
I see.
Yeah. This is not the white point.
Yes.
But it's kind of a time because of symmetric copy of 2 different white points.
Yes.
Positive +1 charge and -1 charge sitting on the same position.
Thank you.
Takeshi,
Yes.
do you need to make assumptions about surface scattering?
Sorry.
Surface scattering. Like in the helium-3 case, specular diffuse scattering, you're making assumptions of that nature in order to get the dispersion of the surface.
Surface scattering. Yeah. So during the surface condition.
Yeah.
Okay. So in this talk we assume the specular perfectly specular. Yes. Okay. So this is one example of the surface bound state in AU pairing state. So here is a phasor particle excitation spectrum on the surface Fourier zone. It might be difficult to see, sorry, but a gray color corresponds to the continuum excitation, which are fully gapped. And inside the gap, there appear several gapless Majorana cone. And this Majorana cone, the Majorana cone on the 2-dimensional surface Fourier zone results in a V-shaped form of the undefined state. V-shaped of the surface denser state. And similar spectrum appears on the 010 surface, but the 001 surface is topological trivial, so there is no characteristic surface state on this surface. So the topological property depending on the orientation of the surface, and of course depending on the gap symmetry. And here is another example, B3U, which has a nodal point on the surface of the cylinder. And as I mentioned before, 010 surface has a nodal point. Nodal point on a pair of nodal points in a surface Fourier zone. And zero energy flat band appears to connect these 2 pairs of point nodes. And actually, the formation of such a zero energy flat band is responsible for the sufficient fraction of the zero energy density state. This peak is very small, but the finite zero energy peak appears at the surface of the surface density state. Okay, so now let's discuss how can we observe such a characteristic dispersion using the STM medium. So this was motivated by a beautiful experiment by Seamus Davis group. They first did a normative STM medium, and what they observed is that they observe only a small dip below TC. But when you use the superconducting tip, then the spectral landscape changes. Actually, the differential channel conductance has a sharp resonant zero bias peak, zero bias conductance peak inside the coherence peak of the superconducting tip. So to understand this beautiful experiment, we try to construct the theory for the tunneling current flowing through the superconducting junction. I'm following the standard formalism from the tunneling Hamiltonian approach. But anyway, this is my Hamiltonian. This Hamiltonian is composed of the Hamiltonian for the 2 separated superconductors, and they are connected by tunneling Hamiltonian. And here, I assume that SC1 is a conventional superconductor, and SC2 is a topological. So the surface of SC2 has a gapless underground state here. So in that situation, we have at least three types of the tunneling process. Single particle tunneling and tunneling of the superfluids, which is nothing but the Josephson current. And the third tunneling process is the Andreeff reflection process, where the pair of electron and the hole in the surface underground state can be converted into the super pair and vice versa. And this all tunneling process can be included in the tunneling current, which is obtained by the Green's function as the interface. And this Green's function contains all information of the all the multiple scattering process of electron and hole as the interface. Yes.
So the picture of that, you have a wherever spin up and spin down in that case, left.
Yes.
The right.
Yeah, yes.
Is that
It's just a schematic picture. And then here, yes. And actually, this is a Josephson current from the between the spin singlet and spin triplet. And usually, such as Josephson current is strongly suppressed because of the orthogonality of spin state. So from now on, we ignore the effect of the Josephson current and focus on the single particle current and Andreeff current. Yeah. Yeah. Okay. So yeah, my numerical calculation takes into account all multiple scattering process. But for simplicity, let's focus on the lowest order contribution, which gives you an expression, well-known expression for the single particle tunneling current, and just a convolution of density of state of the tip and sample. But this single particle tunneling current is strongly suppressed when we consider superconductor-superconductor junction. And the dominant contribution comes from the next order, second lowest order term, which is nothing but the Andreeff reflection process. And here we derive the expression for the Andreeff current, which is valid for the low bias region. But anyway, this expression for the Andreeff current is solely determined by the convolution of the surface density state in the sample superconductor, and the information of the SL superconducting tip appears in the front of the integral as a constant. So in that sense, Andreeff current can capture information of the surface density state in the sample superconductor. Yes.
So the Andreeff current is going to be really suppressed also if there's anything on the surface, or if the Fermi momenta of the two materials are very different. Then you can completely suppress it. So it seems like, you know, you drop one of the thing, and how do you know how strong this will be due to the materials having very different Fermi velocities and the kind of Andreeff reflection you're going to have between like an S wave and some other parameter? It seems really complicated.
It's not planar though. It's not planar. That's the point.
Yeah.
Maybe that's simple.
No, this is for point two. This is the same thing. If you look at just the simple BTK equations, if you just have, yeah, it just looks at the probability of Andreeff reflection. You know, there's a low transmission limit, that is the tunneling limit, and the high transmission limit, which is the Andreeff limit, and everything in between. And if the materials have very different Fermi velocities, or you have to worry about what the direction of the order parameter is.
This is STM, so it's low transmission.
Yeah, well, those are all important parameters. The intrinsic parameters, you know, where the nodes are, what the Fermi velocities are.
Momentum's not conserved in this.
Yes, yeah. We are assuming the point of contact.
Yeah,
The
this holds for point contact.
Does not.
It does. Does too.
Come on, start slapping each other.
Just on the simple BTK, you have this effective barrier. That's the ratio of the Fermi velocities of the two materials, and that gives you the probability of an Andreeff reflection. And also, what happens is the density of states and the order parameter symmetry, they all play a role in point contact spectroscopy. So we can talk afterwards, but they all play a role.
Thank you. Okay, so yes. Yeah. Okay, so before going into the UTe2, let me show the textbook examples of topological superconducting state, say BW state and polar state. The BW state is nothing but a AU pairing state in UTe2, in the sense that the bulk is fully gapped, and the surface has a cone like this one. And here is the surface density of state, which has a double peak structure, and the zero energy density of state is strongly suppressed. But another pairing, the polar state, has a nodal line on the French sphere, and thanks to the nodal line, large fraction of zero energy quasar particle appears on the particular orientation, surface orientation, and this is responsible for the huge zero bias conductance peak on the surface. And let's see what's going on in DADV spectrum in superconducting junction. So this is a numerical result for the DADV in the superconducting junction for the BW pairing state. You can see several characteristic peak and spin structure, and let me explain one by one. And first, this large peak is coming from the single particle tunneling process from this peak in the sample superconductor to this coherence peak in the SL superconducting peak. And another character here, this kink structure originates from the single particle tunneling process from the quasar particle nearly zero energy to the coherence peak in the SL superconductor. And the most remarkable point is that at low bias region, this DIGV spectrum have this kind of the double tube structure, which places a spectrum of the surface density state in a sample superconductor. Okay, so DIV spectrum for the polar pairing state looks like this. This has a sharp peak corresponding to the single particle particle tunneling from here to here. And the point is that, again, at the zero energy, zero bias limit, the sharp peak, small but visible peak, appears as a reflection of this sharp zero bias conductance peak in surface density state. Okay, so now let's move on to the 011 surface of UTe2. 011 surface is naturally privileged surface in UTe2. And here I focus on the one of the cylinder, like this. And for simplicity, we take the gamma point of the in the surface Brillouin zone as the center of the cylinder. And here is a quasar particle dispersion along the disk closed here. And this is a quasar particle dispersion for the AU pairing state, which has a Majorana cone like this. Majorana cone has a highly symmetric point, say gamma point and M point. And of course, this cone is dispersible to all momentum direction. So there is no zero energy peak, but there is a double peak structure here. And this double peak structure reflects the this kind of Van-Hoff singularity along the M gamma line. But anyway, this is a fully gapped pairing state, and the other three are nodal superconducting state. And all these B1U, B2U, B3U have a zero energy fluctuation along a particular direction. For instance, B1U has a zero energy fluctuation along this direction. Okay, so my cylindrical axis is pointing to the M gamma direction. So B1U has a zero energy fluctuation along the cylinder. And this zero energy fluctuation produce the broad zero energy fluctuation, broad zero energy peak in a surface density state. And the B2U also has some segment of the zero energy fluctuation, but this doesn't have any peak structure. Another dip appears in the B2U state. And B3U is something special because the surface density of the state has a sharp, large peak at the zero energy. And this is coming from the fact that tensor particle excitation on the 011 surface in B3U stays nearly flat band, and nearly zero energy flat band extend across the entire region of the 011 surface clearance zone in the case of the B3U. And this nearly flat band, extended flat band, is responsible for the large zero energy peak in the surface tensor state.
Question.
Yes.
Does this take into account the full crystal symmetry of Scotland? The 011 surface left and right are not symmetric, for example.
Yeah.
Is that included in this calculation?
Yeah, actually, my Hamiltonian is very simple Hamiltonian, which doesn't, fully take into account the crystal symmetry. So, so for instance, this kind of dispersion is somewhat accidental because of the simple isometry. So, but some point, for instance, okay, so but at some point, for instance, gamma point and n point, highly symmetric point, this zero energy state is protected by some topological number. And this, of course, this flat band zero energy state also protected by zero energy state, protected by the topological number. So the shape of the this dispersion and peak might be accidental, but some part can be protected by the topological number. Okay. Okay, so this is the DIDV spectrum for the all ADS representations. And what I want to emphasize here is that in a low bias region, this DIDV spectrum captures a characteristic shape of the surface length of state. For instance, AU has a double peak structure, and B1U has a broad peak structure, and so on. The most interesting spectrum appears in the B3U pairing state, which has a three peak structure. And of course, as the central peak originates from the under-reflection between this zero energy tensor particle in the topological superconductor to the SF superconductor. And the different color corresponds to the different values of the hopping energy across the junction. So roughly speaking, the blue corresponds to the low transparency limit. And we can increase the transparency from blue to red. So then this main peak, the intensity of the main peak increases while the intensity of the side peak decreases. The dependence on the transparency is opposite. This can be explained by the the main peak comes from the underlet current, and this is proportional to the T to the fourth. T is a hopping energy across the junction, but the single particle current proportional to the T squared. So if you increase the value of T, the relative weight between the single particle current and the other current can be controlled. And in a cloak transparency limit, this side peak, namely the single particle current, becomes dominant. But when you increase the transparency, this main peak at the zero bias is increased. Okay, now let me compare our result with experimental observation. And here, the DIDV spectrum observed in experiment is in good agreement with B3U pairing. But this is not the end of the story, because the B3U pairing cannot explain the small peak in normal peak SPM. So this reappearing state has a sharp drainage peak in the surface density state. So according to this, the normal peak STM should have this kind of a sharp zero conductance peak, but I cannot explain this inconsistency so far. So further theoretical and experimental studies will be needed. Okay, so far we have discussed. Yes.
Is there any difference between your model and the calculations in the Seamus-Davis paper?
Yeah, actually in the Seamus-Davis paper, they use a simple model for the P-wave superconductor with a spherical plane surface. So it's not a specific model for the UTe2. So because UTe2 has a cylindrical plane surface and more complicated. Yeah,
I see.
Yeah.
So how does that change the theoretical predictions?
Yes, and actually they observed the splitting of the derived conduction peak with changing the transparency or changing the junction resistivity. And according to his calculation, the theory can also reproduce the splitting of the derived conductance peak with changing the resistivity, junction resistivity. But my calculation cannot observe this kind of splitting. Always the weight of the derived conductance peak is gradually changed with changing with transparency.
Thank you.
Yeah. So from theory side, we have some inconsistency with Seamus-Davis paper. So maybe we should solve this inconsistency in future. Okay. So by the way, okay, so from a theoretical standpoint, we can identify the origin of the, for instance, this peak, where this peak comes from, and this peak, for instance, 100% of this peak comes from the single particle something, and so on. The theoretical, we can identify the origin of the peak. But the problem, but the first question is that how can we identify the origin of peaks in experiment? And then the noise spectroscopy can provide useful information on the nature of charge carriers. Okay, so yes, and what I okay, what I consider here is that we monitor the tunneling current flowing through the junction over time, and we take average of the current. And also, we compute the noise-noise correlation. And the key observation is that this time average current and noise power, they are not independent, but rather related to each other through the fluctuation dissipation theory. And we are interested in the shock noise at zero temperature. And then this shock noise, I mean, a current noise ratio, which is called a fun factor, is going to be 2 for the 100 current. And this is distinguishable for the single particle current because the fun factor for the single particle current is going to be 0, 2, so it's going to be 1, and the Josephson current is going to be 0. So fun factor can give you information on the discrete nature of the charge carrier across the junction. Okay, so let me show the bias dependence of the fun factor for the BW state and the polar state. So here's the result. So in the low transparency limit, the fun factor state 1, which means the single particle tunneling process is dominant over the entire bias region. But usually, intuitively, we can expect that this single particle tunneling is strongly suppressed in a low bias region. Because, this is a bit of technical reason, because we need to introduce a small but a finite varying factor to calculate the Green function at the interval. So this physically corresponds to the residual density of space inside the SL gap. And so such a residual density of space leads to the single particle expanding from the residual density of state in a SL side to the surface under the boundary state in the topological side. But again, this single particle current is proportional to the T square, and the under current is T to the fourth. So if you increase the transparency, then the under reflection process becomes dominant, and the fun factor is going to be 2. But drastic behavior appears on the polar phase. So here, visible zero bias conductance peak appears in the DIDB spectrum, and which means that this zero bias conductance peak is significant amount of the under reflection curve. So then the fun factor at the zero bias in the polar state immediately increases with increasing the transparency. So anyway, these two fun factors can give you information on the charge carriers. And yes.
One question, if you go back one. It's just something that's been bothering me for a while. Your DIDV is in arbitrary units, but I would assume in the gap, especially in a calculation, it should be 0. But it's not. It's well off 0. As a matter of fact, you have these things dipping lower outside of the gap. No, it's not. In the middle of the gap. It's not going to 0.
No. This is not going to 0 because of the under reflection from the one side of the space.
Okay, so in this tunneling experiment, because of the Andrea reflection,
Yeah.
Okay, so this is a flattened version of this peak that you were calling the Andrea reflection.
Under reflection of the electron and the hole in the surface state of the superconductor, they are converted into the appear in another side of the
Yeah. All right, and that just prevents me from computationally getting my traditional 0 in the gap.
Yeah.
But it's so flat, but okay, fine.
Okay, so this is my speculation, because calculation of the fun factor in the UTe2 is still ongoing. But anyway, what we can expect from the previous observation is that this zero bias conductance peak in this bias region in which the zero bias conductance peak appears, the fun factor is going to be 2. But outside of this peak, the fun factor is going to be 1. So So the noise spectroscopy can distinguish the physical origins of this peak. Okay, so now let's back to the original question, because we have discussed the density of state, and the density of state can be captured by STM medium. But can we obtain some information on the topological superconducting state beyond the zero bias conductance peak? And what is the signature of topological superconductivity? And answer is that surface Majorana state exhibit anisotropic paramagnetic response. This can be a good signature to identify the topological superconductivity. Okay, so let me take a specific example, AU pairing state and we focus on 011 surface. Okay, so then we have a Majorana cone like this. And the conclusion is that this Majorana cone has a Heisenberg spin, which is always pointing to the surface normal direction. So, which means this surface normal direction means that direction that breaks C2P magnetic rotation symmetry. So let me explain this. So, so let's apply the magnetic field in the plane. Let's say along the b-axis. Then C2 rotation symmetry flips the orientation of the applied magnetic field 180 degrees. But this flipped magnetic field can return to its original position by following the time reversal symmetry. So in that means, so in that sense, any in-plane magnetic field preserves the combination of the C2 rotation and time reversal symmetry. And once you have a magnetic pi rotation symmetry, then this symmetry ensures the existence of the gapless Majorana cone. But you can gap out the magnetic, Majorana cone by applying the magnetic field along the a-axis surface normal direction, because this orientation of the magnetic field explicitly breaks the symmetry. So this means that Majorana cone completely ignore the in-plane magnetic field, only coupled to the surface normal direction. So that's why this Majorana cone has an Heisenberg spin. And this is not only for the AU pairing state, but a more generic argument. And actually, the spin operator constructed by the topological surface state is pointing to the direction that breaks the magnetic symmetry. And this magnetic symmetry originally protects the gapless nature of the Majorana. And I skipped the details of the proof, but we can prove this statement from the particle Hall symmetry and the chiral symmetry and the topological index theorem and so on. Okay, let me show example AU pairing state. So here is the temperature dependence of the surface spin susceptibility. So actually, this is the temperature dependence of the chi AA and the chi BB, chi CC. So chi BB, chi CC is the magnetic response to the in-plane magnetic field. This gradually decreases with lowering the temperature. This is a conventional temperature dependence in a spin-flipped superconductor. But the chi AA is shows anomalous behavior. It increases with lowering the temperature. And this difference between the chi AA and the chi BB comes from the contribution of the surface under bound state. Because chi BB, chi CC, namely, if you apply the in-plane magnetic field, this Majorana cone completely ignore the magnetic field. They do not contribute to the magnetic response. But if you apply the magnetic field along the surface normal direction, then the Majorana cone is gapped out and starts to interaction with the magnetic field. But the interest point is that this contribution of the bound state is always positive and increases with decreasing the temperature. Okay, so this is a summary of the.
Third column. There's no effect because of the cylindrical path.
Yes. Similar, anisotropic magnetic response can be observed on the 010, but cannot observe in on the 001 side. But because this is topological trivial, and there is no surface state, so the magnetic response is just a convention. Okay. So yes, our message is that this kind of the anomalous magnetic response can be a good signature of the topological superconductivity. But we are looking at the very thin region on the surface because we are calculating the local susceptibility on the surface region. And this kind of the anomalous behavior appears in the surface region within the coherence ring. But if you perform, for instance, NMR measurement, you can measure the spin susceptibility, but this is integrated over the sample. So the surface contribution, surface signal is completely ignored. But our idea is as follows. So by coating the surface of UTe2 with a diffusive method, the information of the surface under the boundary state can penetrate into the diffusive metal region within the diffusive length. This is called anomalous proximity effect. Actually, conventional proximity effect is deeply related to the anti reflection of the interface. For instance, in the normal metal, electron is coming to the interface and scattered to the hole. But this scatter to hole brings the information of the phase, superconducting phase in the superconducting side. So, which means that some phase coherence can penetrate into the dirty metal region within the diffusive length. So this is called the proximity effect. And this gives rise to this kind of the characteristic density of state in the dirty metal side. So dirty metal side density of state becomes different. But anomalous if you replace conventional S wave to the topological period pairing state, for instance, the story completely changes because this is the proximity effect of the surface under the boundary state into the dirty normal, but not penetration of the bulk period pairing state. Because the bulk period or parity pairing state is very fragile against the impurities. So impurity immediately kill the period or parity pairing state, but under the boundary state can survive even in the dirty metal region. And this results in a sharp zero-bias conductor peak in a dirty normal metal region. This is what is known as an anomalous proximity. So in that sense, some information of the surface under the boundary state can penetrate into the normal metal region. So our naive expectation is that the signature of Majorana surface state may be amplified by coating the surface of UTe2 with diffusive metal. Okay, so how much time is left?
We started. Okay, that means we've got another half an hour.
So, John asked you said that you said bring spectral dimensions. Physical and local service.
Getting a surface condition, how change that? Okay. Yes. For instance, Majorana is in nature, like anisotropic magnetic response is completely originating from the topological surface state. So if you consider the diffusive, so I think the topological surface state can survive even in such a diffusive surface condition. But another zero energy boundary state appears as a it's like an impurity band can be formed on the in the state. And for instance, so actually in the diffusive limit, the zero energy density of the state increases. But this means that some part of the zero energy density of the state comes from the topological property, but other zero energy state comes from the non-trivial, non-topological process. So they are mixed, and it's difficult to distinguish them, I think. So, so the ideal situation is a specular limit. So the yeah. Okay. So, okay, so let me quickly go through the current status of the HEM3. Yeah. HEM3 is a textbook material of the Fermi leakage and the spin triplet period superfluid phase. And actually, if you cool down to the 2 millikelvin, there appear two superfluid phases for the A phase and B phase. I'm not going to A phase, so if we ignore the A phase, we only focus on the B phase, which is similar to the AU pairing state in UTe2. And this is nothing but the BW pairing state. And thanks to the quantum leakage behavior of the HEM3, the HEM3 has a huge symmetry, 3-dimensional rotation symmetry in spin space and orbital space. So 3 orbital degrees of freedom and 3 spin degrees of freedom of Cooper pairs are highly degenerate. And BW state is a condensation of Cooper pairs with a total angular momentum J equals 0, which means that the Cooper pairs are equally distributed to all orbital and all spin channels. But this has a definite total angular momentum 0, J equals 0. So the resulting gap structure becomes fully isotropic. And this BW phase preserves the SO3 symmetry, and this can be classified to the D3 topological superconductor. And this can be a non-trivial. And the topological nature of this superfluid HEM3 has some similarity to the UTe2. But let me emphasize the difference from the UTe2. Because in the UTe2 or other heavy perennial superconductors, usually have a strong crystalline line field, and also atomic spin orbit coupling is very strong, which reduces the degeneracy of the spin and orbital degrees of freedom of the Cooper pairs. I mean, Cooper pair degrees of freedom are completely frozen up. But this is not the case. HEM3 is different. I mean, as I mentioned before, the 3 spin and 3 orbital degrees of freedom are highly degenerate. Okay, and this huge degrees of freedom of order parameter brings a rich variety of the topological phenomena, like vortices, textures, and domain. Many rich topological defect features are being studied in this HEM3, thanks to this huge high symmetry. But sometimes these huge degrees of freedom in order parameter may be an obstacle for realizing topological space. Why? Because BW space is a condensation of Cooper pair with the J equals 0. But this is a schematic picture of the J equals 0 pair. The Cooper pair, orbital angular momentum of Cooper pair is pointing to the opposite direction of the spin angular momentum. But if you apply the magnetic field, thanks to the huge symmetry, so the orientation of S vector is tilted from the original position to gain the magnetic energy, right? So this means that Cooper pairs can easily reconstruct the orientation of the parameter. And for instance, J equals 0 pair is going to be J equals non-zero pair state. And immediately, topological nature disappears by this reconstruction of the order parameter. So again, let me emphasize that in the bulk HEM3, any tiny magnetic field can kill the topological phase. So any tiny magnetic field can immediately get out the surface under the surface. But here, by confining the HEM3 to the submicron scale, submicron means a length scale comparable to the superfluid for him. By confining the HEM3 to such a very restricted geometry, length scale, this confinement play a role of the crystalline field, which means that the orbital motion of Cooper pairs is fully suppressed in plane. So orbital degeneracy can be lifted by a strong confinement. And similarly, this is very weak, but the HEM3 atom as a nuclear dipole interaction, dipole moment. So dipole-dipole interaction exists, which plays a role of the atomic SOC. So as a consequence of the combination of the confinement and the nuclear dipole interaction, we have this kind of the phase diagram in plane of temperature and magnetic field. We confine M3 to this kind of a distributed geometry where thickness is order of 1 micron. For instance, 10 times larger than the superfluid coherence length. Then what we observe is that there is a critical magnetic field beyond which the system undergoes a topological phase transition. So actually, B1 phase is a topological phase protected by the magnetic pi rotation symmetry, similar to the AU pairing state in the UTe2. But as a critical magnetic field state HC, this magnetic pi rotation is spontaneously broken, and the B phase is going to be topologically triggered. So this HC is a second order phase transition and also simultaneously topological phase transition.
Question?
Yes.
Does the bulk gap close at that transition?
No, you have to stay open.
I see.
So only the order parameter configuration is reconstructed with keeping the bulk gap. Okay, so from the theoretical standpoint, we can establish that B phase can be topological superfluid phase, even in the presence of a magnetic field. So then, can we observe the surface boundary bound state in experiment? So maybe I quickly go through, but as I mentioned at the very beginning of my talk, the Helm-3 was charged neutral, of course. So there is no electric way to close the surface state, like STM and Panel junction and so on. So how can we observe the existence of the surface bound state? And actually, some couple of experimental groups use the micro-mechanical oscillator. I mean, MEMS and MEMS device can be immersed into the liquid of the Helm-3. And here is a schematic picture of the MEMS device. And this central plate can be oscillating laterally. And this resonance frequency is about a few times 10 kilohertz. It's very slowly oscillating. But anyway, this can be immersed into the liquid helium. So this center plate can be surrounded by the helium-3 atoms. So actually, in the superfluid region, the surface bound state can be formed around the center plate. So then you drive the lateral oscillation. This lateral oscillation momentum and the energy can be transferred to the Kessler particle. And the Kessler particle brings the momentum away from the center plate. So this is the origin of the damping of the lateral oscillation of the center plate. And actually, this is a resonance spectrum of the lateral oscillation. And here is a resonance peak, and this is above TC. So if you decrease the temperature approaching the TC, the resonance peak decreases, which is consistent with the temperature dependence of the viscosity. Because according to the textbook, thermoelectric textbook, the viscosity is increases with lowering temperature. So this behavior is consistent with a typical thermoelectric behavior. But when you go to the superfluid region, this peak grows again. So this means that Kessler particle fraction is exponentially decreases with temperature. But the interesting point is that this is a damping rate, namely the width of this resonance spectrum. Initially follows the exponential behavior, but this exponential temperature dependence changes to the power law behavior at sufficiently low temperature. And this change actually comes from the existence of the surface underground state. Yes, because this frequency of the lateral oscillation is order of 10 kilohertz, which is much, much smaller than the frequency scale of the back excitation. So, roughly speaking, this is a STM measure at nearly zero bias speed, nearly zero bias, right? So this temperature dependence change observes the existence of the surface underground state on the diffusive surface. Okay, so actually I calculated the temperature dependence of the laterally oscillating surface, and actually we can reproduce this kind of temperature dependence, initially exponential, but at some sufficiently low temperature, the damping rate follows the power behavior. And this is consistent with damping mechanism due to the surface underground state. Okay, so this is the last part of the talk. And so in a superfluid chemistry, so we can establish where the topological phase, and also we can confirm the existence of surface underground state. Okay, so this is a surface underground state formed in a diffusive surface. So this is not a direct evidence of the topological surface state. So now we want to detect the signal of the topological superfluid. And again, B2 phase is a non-topological phase, and B1 phase is topological phase. So in B1 phase, we can expect that the surface underground state remains gapless, and this surface underground state exhibits anisotropic, eating like anisotropic magnetic response, similarly with UTe2. And so our naive proposal is that this kind of characteristic temperature dependence can be expected in spin susceptibility region. So this is spin susceptibility averaged over the confinement, right? So initially, the susceptibility decreases with temperature, but characteristic temperature T star appears, below which susceptibility increases with lowering the temperature. This increased behavior comes from the contribution of the surface underground state. So this is increasing with temperature. But if you go to the B1 phase, the susceptibility is just follow the conventional behavior. So I mean, there is no contribution from the underground state. So this is a consequence of the heating right factor of the surface underground. And this kind of temperature dependence may be observed in a state of arc experiment. Actually, John Sanders' group succeeded in generating a cavity which is very uniform. The thickness is very uniform. For instance, this is a thickness around 600 or something like that. This is very optimal situation to observe this kind of anomalous behavior of the spin susceptibility. Okay, so let me summarize my talk. In UTe2 and helium-3 share the similar topological properties, of course. But in helium-3, the confinement and nuclear dipole moment act as a weak crystalline field and atomic SOC, and which stabilize the topological phase in the presence of the magnetic field. And in UTe2, we observe the under spectroscopy can be a direct flow for the surface density state in topological superconductor, and time factor can give you some useful information on the charge period. And in Helium 3, our current status is that we could observe the existence of the surface underground state. But so the next target is to identify the topological nature of this surface underground state. So, okay, that's all. Thank you for your attention.
Questions?
In UTe2, you said along the 001 direction, you don't get any surface states.
Yeah.
Is that because along that direction you wait for crystal symmetry that protects the topological order, or you preserve it, but you're just in a trivial phase?
Like 001 surface of the UTe2 is always topological trivial because of the opposite plane surface. The surface is open, so there is no characteristic surface underground state.
And then if you take a 011 cut,
Yeah,
you
yeah,
still
yeah.
get a closed turn surface.
Yes.
All right.
Other questions? Oh, got to keep that stamina going, even though at the end of the day, yes.
So can you be very explicit about the statement you made here off the top? So there is a conflict with current SDM interpretation in your model, and what does it take to solve it or to pin the story down?
Yeah, actually, our nine type. Yeah. So actually, what we observe is that this DIDV spectrum looks perfect agreement with our numerical calculation, but normative measurement has an inconsistency, and maybe of course this comes from the fact that I use a very simple conducting, a simple superconducting gap. So we need more realistic Hamiltonian and realistic superconducting gap. And yes. And otherwise,
In terms of experiment, so there was like, I think that was that noise experiment, would it help to sort it out?
yeah. My suggestion is a noise experiment to help to understand this inconsistency and the physical origin of the peak structure. So, but currently, I don't know why there's such an inconsistency here between the theory and experiment. Even in the theory, we have inconsistency with some states group. So we should solve this problem.
Yes, John.
Did you say at some point that for the candidate order parameters for Murray and Jazero, that you wouldn't expect to see Josephson coupling between S-wave and those order parameters? Could you just expand a little bit?
Yeah, actually, I ignore the Josephson coupling between the S-wave and this UTe2, but this is just an assumption, because if you have some spin orbit coupling as an interface, then such a spin orbit coupling makes the spin singlet to spin triplet. Then the spin Josephson current can flow across the spin triplet in spin singlet superconductor. So, but I don't know how much the SOC exists in impedance.
But in general, there might be other systems with different crystal symmetry which will permit order parameters, some of which would allow Josephson coupling. Is that the
Yes,
case?
right.
Yeah.
Depending on the surface orientation and gap symmetry, the Josephson time can have a strong selection rule.
Do you understand why there is such a weak signal in the superconductor to normal tunneling?
Oh,
I mean, it's a tiny signature.
yes.
Why? What do you have a feeling for why? I mean, it's in your simple theory, it's a big discrepancy. The theory doesn't predict the size of this tiny little. But so why would you? What's your physical understanding of the strong suppression of the gap in the normal to superconducting tunneling?
Oh, sorry.
No, but the effect is only a 5% effect on the overall background density of states, right? Experimentally. What's your physical?
Yeah.
You understand that?
Yeah, like this.
Yes, it's a tiny event. You understand that?
No, no.
No, you don't. No, but the point is the magnitude
Yeah.
is not this, it's this.
It's very
So whether
tiny.
it's a peak or whether it's a dip, it's the size is tiny compared to the predictions.
Well, but whether it's a peak or a dip, that makes also a huge difference.
No, of course,
More
but
than the size.
no, but the point is that the magnitude is tiny, right?
Just to get yelled at again.
Yeah.
If the materials are disparate from point contact spectroscopy, are disparate in their Fermi properties, you get a big suppression of the Andreev signal. Okay, you get a big signal in copper niobium, you get a small signal with copper, cerium, cobalt, and zinc 5. Okay, just because of the Fermi surface parameters.
I see.
That acts like a intrinsic barrier. That's what you were yelling at me about. So,
I never yelled once.
So hang on, there's a difference between point contact spectroscopy and STMs.
this is Andreev spectroscopies, point contact spectroscopies, driving the tip into the surface, right? Isn't it?
No.
This is STM measurement with
It's STM, but if you're looking for Andreev reflection, you have to have a very high transmittance junction. You don't get point contact unless you have you don't get Andreev reflection unless you have a very high transmittance
But
junction.
they're not driving it into the surface. It's
Well,
still,
but they're close enough and have a low transmittance junction, that'll, it's all in that parameter, right? If you fit it, there's this parameter that gives you, but, you just fit it, right? And you might be able to fit it to that, I just don't know. But it's something that takes into account if there's anything at the surface, and if there's Fermi surface parameters that are different, it just goes into, all it is it's an old quasi-classical theory. It's the Bogali-Bogdashen equations. They make some assumptions, including it's an old paper with Blonder, Tinkham, and Clackwood, and it's been used about a bazillion times. And it's used for analyzing tunneling and point contact.
but look, it
between.
is tunneling it. It's tunneling it like crazy. The point is that the gap, the feature is tiny compared to what you'd
Yeah,
expect.
and that's what you mean in our cerium, cobalt, and nim 5s. We couldn't understand why we had a very flat top, yet it was, 10% of what it should be in a perfect Andreev reflection. How would that happen, right?
But in serum cobalt and NIP5 STM, you get, if I remember, you get at least 50% of the normal state. The gap comes in as a huge feature, right? And that's heavy electrons also. So
Yeah, but this is measuring Andreev reflection, and when you look at something like that, there's somewhere in between. Right, there might be something that's suppressing it with a normal tip. And all I would say is that we can talk a second. You could just fit it. It's a real simple theory. We do it all the time, and we have point contact and serum cobalt and 5 and a whole bunch of other things, and the tunneling, and it's hard to tell even in the simple tunneling experiment as a function of temperature or field. You can't really eyeball the gap unless you fit it, right? And so there might be a simple way to fit it and explain some of these differences.
okay,
And that's all.
very good.
Thank you.
Yes, Alex.
It's a brief comment for nucleus. To my understanding, this small feature seen here actually in higher quality samples at lower temperatures, these are very large.
I see.
And a question for the speaker.
Yeah.
So there's a large body of evidence that at low magnetic fields, uranium ditelluride has a fully gapped and analog of the helium-3 phase. Have you considered under pressure or with a large p-axis magnetic field where there's strong evidence that you might have a chiral multi-component triplet?
No, I haven't considered such as oscillators. Yeah. So far, we showed the time reversal symmetry with the because this is a one-dimensional representation. It's different to imagine the spontaneous time reversal symmetry gradient as long as far unless accidental descent occurs. In order to realize the parallel, yeah.
No, you can't get field because the second is.
Okay, so, yeah, no, I have no comment, yeah. We only focus on the very weak in the field.
Okay. That's it for this year. Thank you very much. We'll probably have a, you can get, Jack, one if you want to join us, we'll be down there.
So here, they say thank you.